Hi, I'm Tomáš Iser from Charles University, and today I will show you a simple way to measure the optical properties of translucent materials without any sophisticated and expensive laboratory equipment. It allows anyone to construct a simple setup in which a sample can be placed and its scattering properties can be estimated. This includes albedo, extinction coefficient, and phase function anisotropy. The results are spectrally resolved, leading to high color accuracy and avoiding various problems of RGB rendering, which we can hopefully consider outdated. This is useful whenever we need to simulate real materials, for example in photorealistic volumetric rendering or in optimization pipelines in color 3D printing. Before we introduced our method, several approaches had already existed, which we can categorize into three groups. The goniometric methods rotate a sensor around the sample, capturing its scattering from various angles. This requires expensive rotation stages and complicated calibrations. The second category relies on capturing the backward and forward scattered light using two integrating spheres, which are also expensive optical components. The third category are more affordable setups that rely on standard RGB cameras capturing the material illuminated in a specific way. From the photos, we take a line of pixels corresponding to a one-dimensional brightness curve, which is fitted to material scattering properties. This only works in RGB because a spectrometer can only measure a single point. That brings us to the following question. Can we estimate the light scattering from only a point measurement? The answer is yes, and our paper shows you how. On this picture, 3 cuvettes with water, red wine and milk are placed on a black and white background. As we can see, the color of each material on each background varies with the material's absorption and scattering properties. For example, milk is the only scattering material here, and so it's the only one which appears white on the black background. By simulating this scenario on a computer using Monte Carlo for various albedos and extinction coefficients, we created a two-dimensional diagram which we call the appearance map. The horizontal and vertical axes show the brightness on the black and white backgrounds, respectively. The contours, green to cyan and blue to purple, connect materials with the same albedo and extinction, respectively. On the right, you can see how different positions on the map correspond to different appearances. Since the map is wavelength independent, we can apply it on each wavelength separately, resulting in colored materials. The appearance map encompasses all possible materials of various colors and translucencies, and it is suitable for spectral workflows. Our paper also contains an expansion of this map to 3 dimensions, which allows representing phase functions of various anisotropy coefficients. The key point is that it is very easy to construct a physical setup that would measure exactly the 3 axes of our appearance map. The brightness over the 2 backgrounds is measured by pointing a spectrometer at a diffusely illuminated sample. And the third axis needs a collimated beam to measure transmission. No expensive optical components required. We demonstrate this setup by measuring 3D printing inks. This picture shows a thin magenta sample measured against the white background. The process results in spectrally resolved properties for each of the 5 inks. The accuracy was verified by 3D printing a color checker containing 64 combinations of base inks. Because we measured the inks that the color checker was printed with, we could also simulate its appearance on a computer. We compared the spectra of the virtual color checker to the real physical one. As you can see, our results are very close to reference measurements, both spectrally, visualized by the spectral curves, and in terms of color accuracy, visualized by the sRGB rectangles. Of course, some results showed discrepancies, but even then, the color predictions were close to the references. Moving forward, we would like to extend this method to support fluorescent materials, which is a significant challenge waiting for a simple solution. Thank you, and until next time, see you.